Okay, okay, fine. Okay, so this is the last and final lecture for the supernova part, and let us recap a bit what we were doing in the last two lectures. So today the main discussion would be on different phenomenology that we can do based on our discussions on production of supernova neutrinos and their propagation. So, this is like the very important thing we learned is that like the supernova neutrino emission will be in three phases. We have the neutronization burst, accretion, and the cooling phase for studying oscillation. The first two phases are important because we had large flavor differences, large flux differences among different flavors. In the cooling, it's very similar. And then we realized that these neutrino oscillations in supernovae were non-trivial. You have the neutron-neutron interaction happening very close to the supernova core, and as you go further out, you will have the MSW oscillation. And then we also discussed that this neutron-neutron interaction are mainly of two kinds. The slow collective oscillations, which are happening because of the omega, or basically because of the mass square difference, but it's happening further out, happening at length scale of 100 kilometers. Whereas there is this idea of fast of collective oscillations, where the oscillation is completely run by on neutrino densities. It is in principle independent of the mass or even mass square difference. So in principle, even at the absence of mass square difference, I can still have this kind of oscillations, and they happen at a very small length scale, can happen just outside the neutrino sphere itself. So this is another thing we discussed, like, so we realized that this evolution of these neutrinos or their dynamics is very difficult. We had a 7-dimensional PDEs which are coupled, which are non-linear. So one way of looking at them is linearizing the problem, where you actually look at the off-diagonal elements in the linearized regime and see if they are growing or they are remaining same. If there is exponential growth in the off-diagonal element, which told us like there can be different kind of flavor instabilities. This was the equation which you can get when you linearize the off-diagonal elements, and we realize that these two parameters lambda, which tells us about the electron density, and mu, which is the neutrino density. So these are like your input parameters, or like your model, which your hydrodynamic simulation will give you this lambda and mu, and you want to see what kind of growth you are getting in this off-diagonal element. And then all this we discussed like this very different kinds of oscillation scenarios in normal hierarchy, in inverted hierarchy, under different symmetry arguments can be very well understood from this linearized regime. This is something I did not show yesterday. So this is what was in the inverted ordering, what we used to think as like the slow collective oscillations. And previously, as I mentioned, that in normal ordering there were no oscillations. So this is where this lambda, this is basically the lambda and the mu plane. And in this plane, these are the mu and lambda combinations where you have the flavor instabilities. If your supernova model falls into this zone, you will have this flavor instability, which is basically you can have this collective flavor oscillations. And then we later realize that there can be other kind of instabilities even in normal ordering, and depending on the symmetry argument, whether you take the problem to be azimuthally symmetric or axially symmetric, depending on the symmetry arguments, you can have other instabilities, and this is in the normal ordering. So this is a very common convention that by changing rather than changing the delta m square sign, by changing the lambda and the mu, one can actually, from here it can be shown that by changing the lambda and the mu sign, you can get the other ordering. So this is in the lambda mu plane, this is what is your inverted ordering, and this is the normal ordering, and this kind of explained all these different possibilities people were seeing like in almost 1 decade. that you suddenly have this ordering, have these collective oscillations in inverted ordering. Then you find like you have a certain kind of evolution where you take certain angular information, but you don't see that instability, you see a different kind of possibility. So this is like instability in the sense that what I'm calling instability is that your off-diagonal element in this linearized regime is growing exponentially. So that of course it does not tell you that eventually you will have collective, like whether there is a flavor conversion or not, but this basically tells that in the linearized regime there is a trigger that my off-diagonal element has started growing. But whether this growth is enough to finally give any conversion between the diagonal, the flavor content, that has to be done in the nonlinear picture. So what this picture tells us that like in the lambda mu plane, in this part, if you have a combination of lambda and mu in such, in normal and inverted ordering, you will have your off-diagonal elements growing exponentially, which might lead to flavor conversion. So this was more like an understanding of that, and then we of course discussed that like these neutrinos are tracing different paths, they can have different phases because of the ambient matter, because of the electron. So the electron number density is going to decide whether the slow collective oscillations are suppressed or not. So if the electron densities are larger, then you will have suppression of this collective oscillation. There is the slow kind of collective oscillations and the other way around. And this basically was the picture that for the slow collective oscillation, where I can say like no collective oscillation, because we are only talking about the slow ones. In the early accretion phase, where you want to study any imprint of flavor oscillation, if you take lambda non-zero, if you take the background matter, if you take this, so lambda non-zero means this matter multi-angle effect. If you take this effect, there is no conversion. But if you don't take, you will find the probability changing. So this was these results which kind of helped doing like the phenomenology that you can do with this kind of scenario is that you have to only take the MSW effect. If you only take this Dighe-Smirnov prescription with MSW, you should be able to figure out what kind of fluxes you would expect in the detector. But then that is in the accretion phase. It is a typo. I wrote T less than 500. What it means? The cooling phase, T is greater than 500 milliseconds. But in the cooling phase, this matter multi-angle suppression is not going to happen. So if you want to do any phenomenology with the cooling phase neutrinos, it becomes very complicated because of course you have the multi-angle effect. There is dependence on the flux ordering. This dependence on the flux ordering we learned by one example of the diffuse supernova neutrino background today. So flux ordering means like if you take this neutrino and the anti-neutrino fluxes, their ratios different, you can actually end up in different collective effect results. So I mean like which seems very not very unusual, but the results can be significantly different from one combination to another one. We will show one example of that. And of course, the initial angular distribution of the flavors can also be important. We have also seen this in that the shock effect and turbulence can also be there. And so doing any phenomenology with the cooling phase is not very straightforward. And on top of that, we realize there is this first collective oscillations which were arising because the angular distribution of the different flavor of neutrinos while they are emitting from the star are actually different. And this triggered this whole fast oscillation. So it's basically another kind of instability, but which is triggered from the differences in the angular distribution of the neutrinos. And this, as we mentioned, can even happen for vanishing neutrino masses, but I mean like this I yesterday clarified once, but do not take this message that fast oscillations are happening at vanishing neutrino masses. We know from our other experiment, neutrinos are massive, so it's not fast oscillations are happening means, I mean like that signifies neutrino mass effect is not there. Neutrino mass effect for fast oscillation is also another important aspect which kind of gives you the seed. So, but in principle, fast oscillations can happen even without, even for a vanishing neutrino mass. So the energy information is not very important. So this was the example we saw, that if you have these different angular distributions, and if there's a crossing in the angular distribution, that would mean in this ELN, which is basically the spectra or the difference, flux difference between different flavors, let's say here nu e and nu e bar, if in that spectra there is a crossing, this crossing is going to trigger some kind of this flavor instability, which is giving this fast collective oscillation. For the slow collective oscillation, this is the angular, this is the spectra, but not in the angular one, but in energy. So in the energy spectra, if the spectra of the neutrinos and antineutrinos, if there is a crossing among them, that can trigger what you have seen as the slow collective oscillation. Yeah, so this is the zero crossing in the energy spectra. Like this, you can have these slow collective oscillations, which were happening at few hundred kilometers. And again, like here I did not give the example, but yesterday we discussed that these collective oscillations, the fast ones are happening at a centimeter length scale or at nanosecond time scale. Then the question comes, okay, so this was like another important thing, that these first collective oscillations are actually three flavor effect, that it is not enough to take the difference between nu e and nu e bar, you have to also consider the muon neutrinos or the tau neutrinos if they are there, and indeed they are there, they are in the muon hydrodynamic simulations where people were able to create muons in the supernova environment. There were differences in the muon and the anti-muon fluxes, and which basically gave the idea that these fast oscillations are indeed actually a three flavor effect, where you have to consider the muons as well. And then we learned like where are these fast oscillations happening, which is still something we are trying to understand. But in this muon simulation results, where these are the positions where these crossings in the spectra were happening, and this is the failing shock radius, and all of them are happening farther out from the shock radius. So far away from the neutrinosphere, around the shock front, there are other proposals that we have seen where this can even happen behind the shock front, or can happen for different reasons, that basically this crossing in the spectra can come from many different physics inside the star. So now the question is, with this kind of understanding of the neutrino oscillation, what kind of phenomenology that one can do? What are the things we can study? Let's say our understanding of the fast oscillation is still growing. We do not have a complete information. There are a lot of things to figure out. So meanwhile, what can we actually do? So we have realized that these fluxes are different in these different phases. So is the oscillation picture. So for example, the neutronization burst phase, which has the extremely large flavor difference, will not have any kind of self-induced oscillation. Because of this large flavor difference, you cannot trigger this self-induced oscillation. You cannot have this lepton final conservation of this electron number is so high that so this flavor conversion cannot take care of this large flavor asymmetry. So in the neutronization burst phase, if you are doing any phenomenology with that, you don't have to bother about the self-induced oscillation. You are safe only in the MSW regime. So this is like one phase, but then how robust is this phase? That is a 50 millisecond phase. Am I really going to see such a phase? So this is something I mentioned the other day. It's called the standard candle for the supernova neutrinos. What meant by standard candle? Here you can see examples with many different equation of state, the difference equation of state, the difference in the neutrino transport mechanism, and different progenitor masses. So this is from the first results where people started looking into the neutronization burst phase more carefully. You can see that for all of these differences in the input of your hydrodynamic simulation, you are getting this phase which is very robust and very similar fluxes. And this is from the Garking group, but of course other groups, other hydrodynamic simulation groups also looked into it, and they have found very similar results. So this is like a standard candle. So in the other phases, you maybe do not know from the hydrodynamic simulation input what are the exact fluxes. There might be differences depending on the progenitors, but here this is very standard compared to the other phases. So this is considered to be the standard candle, and on top of that you have the advantage that you can only do MSW oscillation. So if you do that, this is something, as you know, like for in Dune and also in Hyper K. So you really need big detector like Hyper K, because Hyper K, if you remember, we mentioned this is the inverse beta decay detector, water Cherenkov detector. But then you can still detect the electron neutrinos in this or the other flavors with the scattering of the electrons. But then there is the problem of like putting a cut, because these are like coming as a in the background of the inverse beta decay process, right? But in the initial phase, you actually barely do not have many electron anti-neutrino. So here you can see for Hyper K, how would that phase actually look like? But then if you are only doing MSW oscillation with this neutronization burst phase, your fluxes in the normal and inverted ordering are really different. So as you can see, the normal ordering, the flux is depending only on the X flavor, and if you remember this one, your X flavor is almost missing in here. So the peak is only in the nu E. So your flux at the detector is basically the flux, the initial flux of the X flavor at the source, and which is almost zero. So you are actually not going to see this peak in the normal ordering. On the other hand, you can see in the inverted ordering, this flux depends on nu x, of course, but also depends on the nu e flux from the oscillation picture, and with of course the angle square is also coming in here. But then since I had this nu e is present there, in the inverted ordering I am going to see this peak. And of course Dune or a liquid argon TPC being electron neutrino detector should be able to detect it, and so is the water Cherenkov detector. So basically this can be a sure. So this is like example with a 10 kiloparsec one. So this is like a galactic one, but not very close, reasonably far away. So this is for a 10 kpc star. All these examples that we are going to see in this phenomenology part are actually with a 10 kiloparsec distant star. So for that one, the peak will be missing in the normal ordering, but you should be able to see the peak in the inverted ordering. But yes, this is coming from the MSW from. So this flux expression, what I showed yesterday, if you just take the MSW oscillation and you have your knowledge of the mixing tricks, you should be able to give you what kind of jump probability you can have inside the star. If you take that, you are going to get these expressions. Now, but this actually allows you to do even further interesting things. For example, you are able to study things like, say, like the speed of the neutrinos. For example, if there is a violation of Lorentz invariance, this is like one example. So this neutronization peak has been used for many different phenomenology. There is a wide range of papers on that. So this is from one of our work. This is just an example. There are many such examples. So like if you take this velocity difference is actually dependent on the energy of the neutrinos. Then the ones which are coming faster will actually have a very different signature, because as you can see, these are like subluminal, they are coming later. So this peak is actually getting smeared out, going farther out. In the normal ordering, there is no peak, but it also gets like delayed. On the other hand, if it is like coming faster than the light, you will actually have a difference in the peak, but which will come faster. But then, since this depends on the energy, so the neutrinos coming, probably they left at the same time, but they will reach you at different epoch, right? So this bins would actually get smeared out. So from there, one can actually put a very strong bound on these differences of these neutrinos from any observation of simply from the observation of the peak, or let's from the smearing effect, one can get such a result. Similar thing you can also think in terms of sterile neutrinos, right? If you have active sterile EV square oscillation, you can see this paper. There are also like Pasquale and Arman, they have also done analysis with heavy sterile also. So there are like long analysis on that, but here you will have a similar phenomenology that your peak in the inverted ordering can actually, so if there are sterile neutrinos and if these neutrinos have converted into them, you can actually show that this peak, simply the appearance of the peak for inverted ordering will simply negate a large part of the sterile neutrino parameter space. So these are like things one can do. So this is like, as you see, like this is still examples with the what we called as the neutrino light curve, that the variation of the neutrino flux with time. Another such example is what one can do in the accretion phase. So what is happening in the accretion phase? Similarly, so previously I was in the neutronization one, I was writing the fluxes for the electron neutrinos, and now I'm writing the fluxes for the electron antineutrinos. And as you can see, the electron antineutrino flux in the inverted ordering completely depends on the nu x fluxes, and the other way around for the normal one. Now, as we saw in the neutronization burst phase, there was a difference between the nu x and the nu e and the nu e bar fluxes. Here is also was a slight delay between like a difference of fluxes, or like the growth time coming into the nu e and the nu x. The reason is straightforward, is that like for the nu e and nu e bar, you have a high degeneracy and it suppresses the nu e bar production. Or also you can think like the nu e bar is more in equilibrium compared to the nu x because of all the different kind of interactions it can have compared to the nu x. So the flux of nu x rises faster. So nu x leaves faster from the star compared to the nu e bar. And so these are the flux for the nu x and the I think the nu x and the so this is the nu x, this is probably nu e. Okay, I cannot see myself very well. Yeah, so the nu x rises faster, so it should be the nu x, it should be the nu e. So it might seem a very small difference among the flux. So this is what we are calling the rise time of this flux. So it eventually would mean, in principle, the flux in inverted ordering would rise faster than the normal ordering. But can we really do that, see this thing phenomenologically, like what happens? And of course, as you can see, I am still talking about only MSW effect, and this is with the assumption that, so if you want to really do this phenomenology today's time, you have to assume that of course these slow collective oscillations are matter suppressed, but the fast oscillations we are not settled, and let's say I do not have a scenario of fast oscillation. If I do not have such a scenario, then only this analysis is possible, and this is results from Christian Note. He also checked the same thing, and what found here is, like, as you can see, this as the time progresses. So here you can see how the fluxes of one flavor compared to, here is basically normalized flux. So this is the normalized count rate he is looking at, and found that there is a difference among the rise of like for a typical case, like for this case, you can see the rise is slower compared to this one. So basically this slope is different. And then if you look into these things more carefully, this event growth rate, or let's say rise time of it for ice cube, you clearly see that the normal and the inverted ordering, there is a clear separation among them. The same thing from our original proposal is, like, as you can see, in the for ice cube, in the normal and the inverted ordering, there is a flux difference, and which is basically the root n errors. And there the point is whether one can distinguish these differences or not. And again, like if you take this normalized count rate with this event ratio, you see there will be a clear separation between normal and the inverted ordering. And this is something also we are working with Avinash and Munmun. We are trying to replicate these results for the hyper K. And so this is like the two examples of the time spectra that we saw. This is the final example of the diffuse supernova neutrino background. You'll have a much more detailed discussion on DSNB from Ranjan. But let me just introduce it for as an example. We're going to talk about DSNB, right? Yes, yeah, okay. Yeah, but this here consider it like an example of what can happen to the energy spectra. So the last two examples we saw was for the time spectra, but what can happen for the energy spectra? We discussed in very briefly on the first lecture about DSNB. What was DSNB? It's like the collection of all these neutrinos from all the past supernovae, right? So this is a redshifted one. It goes to a lower energies. Here there are backgrounds like antineutrinos. For example, this is for super K, and the atmospheric background. There is also this invisible muons. So eventually, this flux will come like a small, let's say, modulation on the total background. And that's what they are trying to look at, and it becomes much easier if you have the neutron tagging in the inverse beta decay to distinguish from the background. And this is this GDSK proposal, which is currently running in super K. And this is a very simple way of understanding how to calculate this flux. So this is the rate of the supernova happening over the universe, which is changing with the redshift, which can also depend on the mass. And this is the flux of the neutrinos from each supernova. So I think we will discuss this thing after the first lecture, that what flux should go in. So this is a time integrated flux. This is the flux from not from from neutronization burst, accretion or cooling, but you integrate over the whole flux and you figure out how many neutrinos are there at which energy. So basically get the time integrated spectra which will go in here. And of course, this can also depend on the mass of the progenitor. This comes from the cosmological factors, and you have to integrate over all the redshifts for that. But then, since you want to also look at the mass dependence, one should also look into integrate over all the possible masses of supernovae. Here we are looking from say 10 solar mass to 125.1. What about the supernova rate? The supernova rate, it is assumed that is actually proportional to the star formation rate, and we have some measure of the star formation rate. But something else will also come in the initial mass function, like what is the distribution of the supernovae on different masses. So these are the information. What you would require, you would also require what is the local supernova rate, because if you want to normalize it. So this is something like 10 to the power minus 4. Now there are a lot of uncertainties while you try to calculate it. There will be uncertainties for the star formation rate, for this local supernovae rate, apart from the oscillation scenarios. But there is another very important uncertainty which will come up, is basically so let's go back to this picture. Say we were assuming that the neutrinos, you remember what we discussed the other day, that here is basically the shock is stalled, and since we see core collapse events, we are assuming that the shock is somehow definitely is going to throw away the mantle, will have the cooling phase. But what we keep seeing in simulations is that the shock is not growing and we have a failed event. So this is called the failed supernovae, or what you call the supernova which results in a black hole. But as you can understand, even for the failed supernovae, the first half second neutrinos will come out. So you may not see the cooling phase, but for a failed supernova, you should be able to see the first half second neutrinos. And as you can see here, I did not put the average energies of them. So it's not only the luminosity which changes, their average energies from different phases are would also change. So therefore, if you want to look at the time integrated spectra for a black hole forming supernovae, let's not call it supernovae, a black hole forming star and a neutron star forming star on a progenitor. So there will be differences in their time integrated energy spectra at the different average energies. But then we do not know what fraction of these supernovae or what fraction of these masses between 10 to 125, this is my integration limit, what fraction of these stars actually had become black holes in history and what fraction has become neutron star forming one. And that is again comes from the hydrodynamic simulation, where they vary the mass of the progenitor and see what fraction is going to come up. So here is a result from my group. So my student is doing this calculation. So here you can see for different cases for the neutron star forming and then the black hole forming case. So these are the different cases, means you take different fraction of this black hole forming star, which the information comes from the hydrodynamic simulation. So if you take a larger fraction and a smaller fraction, what would change in this case? So like let's look into one of these results. Let's say the case 1, that is 44% are basically, let's say, black hole forming. Then this low energy one, where the average energy at a lower value, this one is coming from the neutron star ones. But as I already explained that for the black hole ones, the average energy is larger because it's coming from the accretion phase. All these neutrinos are mostly emitted in the accretion phase, where they are coming from the created from the thermal burst, and the thermal bath had a higher energy. They should have a larger average energy. So now, of course, it would have been great if you could have detected both these components. One is harder and one is softer. But this is a phenomenology that one can do. But then you of course understood, like this is again like the uncertainty from the astrophysics. But another uncertainty from the astrophysics is what kind of oscillation scenario I am going to take. And this is one example which we studied long time back, which Srubabati was also in that paper. And we studied that, we found that this is mostly in the cooling phase what would happen. That what we are varying here, these numbers are basically different fractions of neutrinos compared to antineutrinos. So basically, your initial input number of the neutrino and antineutrino is different. If you have them, you have many different signals. Here I am plotting the probability with energy, and you can see in certain cases the probability changes once from 1 to 0. In certain cases, it changes again. So this is we are calling the single and a double split pattern. There can be even multiple split pattern in the spectra. So your energy spectra, depending on your input, can be very different, and in the whole cooling phase, as these numbers will keep changing, you might have a very different oscillation scenario compared to other. And since now you are doing the whole time integrated spectra, you have to look into for all these spectra. This information is very important. And we tried to replicate something like that in the very beginning, the first attempt for looking at the DSNB, but with the variation of this progenitor. Since at that time nobody had the information, we took some kind of a log normal distribution for the supernovae parameters from some range given in the hydrodynamic simulation literature at that time. And definitely, as you can see, this phi r nu e, which tells you what fraction of, what is the ratio for phi r nu e to phi r nu e bar. Here I have given the phi r nu e bar, which is basically the electron antineutrino initial number, let's say. And as you can change it, as you can see, the number of events in the inverter and the normal ordering, they keep changing. And this is like the dash ones for a different model of the for this distribution of the parameters. And after that, people looked into this thing in more detail. For example, Irene looked into it. So what they did, they took 3 different progenitor classes, and they looked into 3 different time steps of the progenitor, and looked at whatever is the oscillation coming at that time step. They took it to be representative for a certain range of the star. So basically, they took and they did this calculation with 3 ones, and they also found that the results might change on different kind of progenitors or different inputs in the cooling phase. And recently, this study has been done, a very detailed study from the Garkin group, where they looked into 200 different progenitors, looked into many different kind of uncertainties, for example, fraction of supernovae, neutron star Mach limit, etc., and the star formation. So all these different uncertainties they looked into, and this is their best case scenario, and this is something what we are trying to do with our model. And this is also a model, but with real running of the hydrodynamic simulation. And as you can understand why people have put so much of effort, like running 200 progenitors, because the GDSK is running, and according to the estimate, the DSNB would be detectable within 5 years of detection running. Ranjan will give much more detail on that. So this is something, just an example, if you want to do phenomenology with supernova neutrinos in the energy spectra, how these things are going to change. So this kind of completes our discussion. We learned how the neutrinos are produced, what are the problems in the supernova hydrodynamic simulations, what are the possible ways neutrinos can help them. We did a long discussion on the neutrino propagation. We found that the dense neutrino background is very important, but yet there are certain phenomenology one can still do without the knowledge of the collective oscillations. And then finally, I will just touch up another part which Ranjan is going to do a much more detailed discussion. But so this is like so initially I thought like I will just do like an introduction and he will do better, but he will actually do the introduction. So, but I will cover like only 2 or 3 slides from here. So, what is the idea? Rami's also discussed this yesterday. But you had these GZK neutrinos, this Greitzen-Zatspen-Kuzmin process. What is the idea? Idea is that like you have very high energy cosmic rays coming from some astrophysical sources. While coming, they will interact with the CMB, the cosmic microwave background, and that can create this P gamma interaction, which will have this usual shower. You will have these photons and these all these neutrino species. Now the photons which are created in this process while coming, they will still interact with other background, but the neutrinos will come directly. And this will open up something like another scenario of the multi-messenger astronomy, or here in case of multi-messenger cosmic ray studies, where detecting one would actually give you information about the other. And this is the process, proton with gamma CMB create these pions gives you these things. So what would mean, this is actually, at that time it was also known as the GZK anomaly. What was the idea? Idea was that this process has a very high threshold, almost like close to 10 to the power 20 eV. So any cosmic ray above that energy should not be coming to us, right? So all of them should get in the GZK process, should get away. So they are not so we are not transparent to cosmic rays to these energies. And while in the propagation of the gamma rays, what would happen is that this gamma, which when they are coming from this process, will still interact with the background CMB and also something called the extragalactic radio background. And you should be, this attenuation of the gamma is bit non-trivial. That has to be done in like, I mean, very not so easy to run. And there are certain packages and where these ultra energy neutrinos can be treated. And this is like an example what would happen. So here you see, this is the extragalactic radio background, this is the CMB, and these photons from the GZK while coming, they are interacting. This is like, let's say this was the initial flux of the proton. We take something like a E square flux, and once you propagate, so your proton flux would look something like this black line, and we have just simply normalized it to the Auger and High-Risk result from the cosmic rays. Here what you are seeing is cosmic rays with energies at very high energy, and with this, so this is how we figured out the normalization. But then the other particles which are produced here, as shown here, you can see this is the gamma. So here is the your source, here is the GZK protons, and this is the gamma without any loss. So this is the gamma which will come if you do not have this loss from gamma CMB and gamma ERB. And then if you have these losses, you can see that this gamma flux will come further down if you take with CMB. If you take this extragalactic radio background component, you will have it further down there. But the neutrinos which are given in this blue line will not have any propagation effect. So your initial gamma flux coming from these protons interacting with the background CMB would finally come down to this low energy because of the propagation. And of course, there are like uncertainties in this extragalactic radio background. I will not go in details of that. Ranjan is going to cover that. I will also skip this slide. But here is the result that we found for these scenarios. So here you can see the neutrino, the GZK neutrino background and GZK photon background, and all the different running experiments for the neutrinos are up here. So this background is below these running experiments background, their sensitivities. However, ice cube Gen 2 and grand 200K would be able to detect these neutrinos, because if these future experiments come, this prediction of the GZK neutrino flux is almost 1 order larger than that. However, this prediction, as you can see, something written proton. So here we are taking that the cosmic rays are mostly proton, but if the cosmic rays have other heavier elements like iron, we did the another extreme case where you can see that the iron, if you have like, so this is 100% iron case, which is also another extreme, what would happen, something in between these two cases, right? So, but even for the iron case at low energies, as you can see, it's above the ice cube Gen 2 sensitivity. So, if ice cube Gen 2 becomes feasible, this neutrino flux from the GZK process should be detected, and the corresponding gamma flux for the proton and the iron case is also shown here. And here you can see the present limits from the running experiments, and these are the upcoming limits from OJ and Grand. So they should also be detectable. But then this takes us to another interesting scenario. So this is your neutrino flux. So before we are putting it into different slides, because you can see that the y-axis we have different. Here this is the E flux, this is the E square flux. But now we have put them together, the neutrino and the gamma ray flux, and this is the ice cube limit. But then let's say ice cube is not able to see these GZK neutrinos. What would that tell me about the gamma rays from that part, right? So this is what we are putting as the ice cube Gen 2 limit, but on the gamma rays, and this limit corresponding to this ice cube limit, the gamma ray limit, comes out somewhere here, which is below the prediction of the gamma rays. So in principle, if we see these ice cube neutrinos, we should be also able to see these if we see the GZK neutrinos in ice cube, we should also be able to see the GZK gammas in the gamma ray detectors. But if you do not see them, that actually tell us in future that the GZK gamma flux is actually below this limit. So this is what you can do with a multi-messenger astronomy, and we have seen two examples of multi-messenger astronomy, one with the supernovae, another which is at MeV energies. This example is at the extreme energies like in 10 to the power 20 eV, and this basically the end of our discussion. So we learnt about the supernova neutrinos and their production, propagation, detection. We have this review which I would like to advertise to you, and it covers like all these three parts, and which has a very long discussion, which has like, if you are very interested in the hydrodynamic simulation, this covers that. It also covers the oscillation and the production part. So this can be a good starting point. There are many other reviews which has come up after that, because this is, you can see in 2015, which did not cover the fast oscillation. So the fast oscillation, if you want to look into that, this is not where you should look at, but there are recent reviews on fast oscillation as well. But apart from that, if you are interested in supernova neutrino phenomenology, this should be a good starting point for you. Thank you.
Okay, so some questions.
So I have seen so many models for the supernova, like there are so many models, and you are basically talking about Garching models, but not only Garching model, there are so many models. So can you please shed on some light, like which one will be the robust one for recent calculations?
It's a very sensitive thing. Okay. If you ask every group, they will say like, we have these advantages. People are genuine. They will not say mine is the best, but they will say these are my advantages, these are their advantages. So the Garking ones are like the way in my group and the way my collaborator looks at the standard one. It's more detailed in some sense, and the result you see there are more robust, going from one case to another case. There is these Japanese groups, they also do these things, but there are certain effects which are not seen in those. For example, yesterday I was showing that this average energies of this. So if you look at the 1987 data, and if you look into it, you will find that the average energies are lower, And say like when I was doing my PhD 10-15 years back, these numbers were like almost double what the simulations were predicting. So if you go to the groups in Japan, their average energies are still higher. But for these groups based in Europe, there's a group in like now in Poland of Tobias Fischer who is running that one, and the people in there are people in GSI, there are people in Sogarking. So all of their results kind of gives this low energy, low average energy one. So are the American ones. So now it actually depends what you are studying and what kind of phenomenology that you want to do. On that you can choose like what group to write for their data. So for example, like if you're doing something which is a long-term simulation, so like 1D simulation is probably enough. So you can, many of the groups will give you similar results, but you can see that I have seen like for some of these results from the Japanese collaborators are the average energy still higher. And that we have, I think probably we were there, like we're discussing that this actually means that how they are treating the particle processes inside. If you have more interactions, the particles will leave later and you will have a lower average energy. If your code is not taking it as a whole, if there are like lesser processes, your particles will diffuse out earlier and you will have a higher average energy. So it's not to criticize anyone, but every simulation has its own benefits. For example, like for this fast oscillations, what you need is the angular information. You want to know how many neutrinos left the star at which angle. So many groups may not even have. For that you need at least a 2D simulation. So people who are doing 1D is not good enough. So like now people are doing 3D, but those 3D probably are not precise enough. The beams are probably larger. They will give you angular information in a wide angle, and you probably need something smaller. So this is depending on the scenario. You can contact these groups.
And here in some slides also you have shown that Tambora was there. So Tambora is basically taking the Livermore model as far I know.
Wait, let me go back.
I think in some slides the name was there. Yeah, that one also. Yes, Tambora.
No, this was actually with Basel simulation. This is actually Tobias Fischer's simulation.
Okay.
And what they did is like, so the simulation is not important, rather in this case actually what is like, you can see the uncertainty coming from the oscillation part, not the absolute uncertainty, but the like theoretical uncertainty that you can get. As you have seen, like this whole spectral split pattern can be very different depending on what is your input. So now in principle one should actually be doing, let's look here. Yeah, so one should actually be doing this. So for every snapshot of the cooling phase, let's forget about the accretion phase. If you just think like, okay, collective oscillations are suppressed here, you are safe. But here it's not suppressed. So now at every time snap, your nu x, nu e and nu e bar ratio is changing. So you should be running a self-induced code for this collective oscillation code for each and every point, because the result can be different, and then you should actually do a time integration on that. So what people were doing, they just took like 3 time snaps and took, say, like whatever is the result at 2 seconds is indicative of whatever happened before 2 seconds. 2 to 4 this way. What can people do? Like these are like really numerically expensive. So that's the first trial, and of course now people are doing better, and we hope like you people will do even better than this.